Wow, I haven't even started yet. Cool. Hi, everyone. Welcome to the talk on CrowdSim 3D, a crowd simulation add-on for Blender. I'm Monique, and I'm here with Jeroen. We're from AtMind. We're Blender developers. We've been Blender developers for a while. We wrote a blend file parser way back. After that, we wrote the Blender capacitor. We set up a website, B3 101, to teach young students Blender. Jeroen this year worked on the Workbench engine, and together we wrote a crowd simulation add-on. So before I dig into the details of the crowd simulation, I want to show you a short video that presents the features of the crowd simulation. I do have to apologize. Sorry, the crowd simulation uses very basic characters and motions. That's not because of the crowd simulation, that's just a lack of my artistic skills. I'm a developer. But the idea is to show you the features, to show you how to create your characters, how to create varieties of your characters, how to configure your meshes and your materials, creating different characters for your crowds, but also how to add behavior to your crowd so that they behaved in a way that you want. So we'll show you a video. The crowd simulation works for Blender 279 and uses cycles.
Nee, je moet. Okay, thank you for the applause. Let's the rest of the presentation we're going into a bit more detail what kind of what the CrowdSim can do for you, and then more in the functionality it has. Well, mainly the first things that differs is you want to add a crowd to your scene. And let's go over to that, because we developed some tools which really can help you doing that. Basically, you can add a crowd to your scene by well, we're using agents, and an agent is something like a placeholder where you can put your put an object into, but also an armature with all its meshes. And you can do it doing a single agent at a time, but like the example on the screen, you can also use something we call the factory, and the factory will create a lot of agents for you in the scene, and you can select what kind of formation you want to use. This example uses the grid formation, which really adds the agents in rows and columns. But we can also do it in a plane or a circle or a triangle, or even you can add your own shape, and the agents will be placed in that shape. Next to the shape, you can also say from, okay, what kind of formation do you want in that shape? Is it a grid formation or randomized? Are those aligned? And we have several options for that. When you have the agents in your scene, you want to something that we call populated, and that means, okay, we have a lot of agents. What are placeholders, and we want to fill it with the objects you want, and you can configure your own model for that. And when you do that, you can specify how you want to change your materials amongst different agents, but also like if you have an armature which with a person, you can say from, oh, I want that armature to have, or that object to have a glass or not a glass, adding items to it. You can also variate with those. And we're using a node tree editor for that. And basically, it gives you full control over everything that's being populated. And even after you have populated your scene, you can go to an agent and say from, okay, this agent, I want to have this kind of look. Well, basically, it all sounds simple, but have you ever tried to add a single armature and duplicate it in your blend file? It's hard. And that's basically because there are two things that's limiting you. One thing is the proxy system. The current proxy system can only handle a single version of an armature, but we solved that. And even if you have a single version of your armature, the materials and the meshes are connected. And even here you see that we change the materials of all those objects. So now we have a crowd, but that crowd is standing still, and we want to add some behavior to it. We want to add some life to it. And how do we do that? Well, Python scripting? No. We also use a node-based system for that. So we looked at several systems, and the most widely used one is behavior trees. And behavior trees has been invented in the 1980s for handling the logic of robots. But even modern game engines on Unreal uses behavior trees. And behavior trees is a node-based system, and you can you can assign behavior to an agent you have in the scene, and still being able to control the agent on a really detailed level, like specifically say from, okay, for this agent it is different. But you can also say from, okay, I don't want to do it in this specific state, but on a group of agents or a subgroup of the agents in your scene, or even if your agent has a specific item or a specific state. That's why we added at this point 40 nodes, but we're still adding new nodes to it. We have nodes to add state to an agent, and you can think about how much life do I have, or how much damage can I take. But even social things like, okay, do I fear? How do I deal with fear? Next to the targets, next to the states, we also have targets, and targets are goals where you want to walk to, or you want to look at, or it could be a door. I want to walk to a door to open it, and you can say to that agent, okay, walk to that door. Then the door is a target. I also said briefly about movement. You want to walk to the door, so we have we can use navigation meshes, and based on this navigation meshes, the agent can find its paths to the door. And something we're going to talk about in a few minutes is about collisions and avoidance. So. That's a really important one. If you have a crowd, you don't want those agents to bump into each other. The result of the behavior trees, those are stored in animation actions in the when you have executed the tree. And we only store at this point the location and the orientation of the agents. So we still don't have any animation. How does he move towards the door? And we came up with a system, and that system will allows you to automatically merge animation actions to a really believable animations that will be rendered. And during the behavior tree, we have a node where you can assign specific actions and animation actions as being a walk cycle to an agent. So you can have an agent which is a child, which walks totally different than a man or an elder, or even dogs or other animals. You can also do that based on the state. How much health do you have? Do you want different walk cycles for that? And then the magic happens. Based on the location and the rotation of that agent, we are going to generate a walk cycle from it. Every action, the artist can say from, okay, this action is basically using an animation when you walk 1.5 meters per second and don't rotate anything. In the center graph, you see from bottom to top. The bottom is when you stand still, and the top of the graph, that is when you move with 2 meters per second. On the center of the if you go to the x-axis, on the center of the graph, you're not turning. And from center to right, it is from, okay, how fast am I turning to the right side? And on the left, it is how fast am I turning to the right side. The red dot in the middle, that states from, okay, this is the actual speed of the agent in the scene, in the animation you have. And the green dots say from, okay, how much influence does that animation action have in your final generated action? The result of this is stored in the NLA editor. So no caching at this point. It is all just in Blender animation system. So I'm going to give the microphone to you again.
Thank you. And yes, the graph you saw is a graph we internally use to calculate the movement. A bit about collision avoidance. So in the CrowdSim, we have a node, well, we have several nodes, to program or configure how agents should avoid each other. We also have a node that sometimes you want agents to collide to have a certain effect. We have that node as well. But if you want to have crowds walking against each other, you don't want them to collide. The CrowdSim 3D supports 4 collision algorithms. Why 4? Well, because there isn't one algorithm that fits all types of simulations. So yes, for your simulation, you have to look which type of algorithm fits best. Well, we support at least what I call the industry standard algorithm, or maybe I should say widely used algorithm. One is the ORCA lines, and the other one is the time to collision. ORCA lines, also known as RVO2, basically uses an algebraic approach towards collisions, towards collision avoidance, but sometimes has the effect of what I call agents becoming afraid. And I'll show an example in the next slide. The time to collision is more a force-based algorithm, but will perform better if you put in much subframes. And it only considers agents that are inside. And it just calculates the forces between the agents inside. There are 2 more algorithms, if it works. Everything okay? This doesn't seem to respond anymore. Yes, now it does. We have a very basic, what I call radar algorithm, that just looks from a certain angle and decides what is the safest route. Safest meaning the chance of colliding is the lowest. And we have a very basic force-based algorithm that will look at all the surrounding agents, different from the time to collision algorithm, which is only looking at agents inside. This force-based algorithm will have a look at all surrounding agents. So, just to give you an example, here you see 2 groups of agents, 2 factories, walking into each other. What do you think? Which one performs best? It's difficult to say, right? I think the RVO2 has more the natural kind of behavior, where you see the force-based algorithm and the radar algorithms, they will spread. They walk out, they scatter, and then they try to walk around each other, and sometimes they circle around each other. So the RVO2 would probably perform best when in balanced group. By the way, in this example and in the following examples, I'm using this algorithm with default parameters, meaning also in the crowd simulation, you can tweak these algorithms. You can play with the parameters of these algorithms, but this is basically to show you the differences in the type of simulation that you can get using these algorithms. So this is, for instance, if you have 2 equal groups walking into each other. What if you have 2 agents walking into a group of people? And this is what I call with RVO2 being afraid. You see the blue agents in the RVO2 model, they kind of stop moving in their direction and they move with the red ones. And that's what I mean with they become kind of like afraid. Again, the force-based algorithms, they again spread and then try to walk around each other. What would be the best algorithm here? I'm not sure. Maybe the radar? I don't know. It's quite hard to say. How about walking into a wall of people? There you see the RVO2, the Orca lines. They kind of get stuck into the other ones. And where the force-based algorithms and the radar perform better because they look forward based on the forces. They walk around the wall of people. How about obstacles? There you see the Orca lines having a bit more natural simulation. The other ones a bit less, but perhaps with some tweaking, the force-based algorithms could perform a little bit better. So what's the takeaway from these 4 algorithms? Yes, it really depends on your crowd simulation. What type of simulation do you have? What type of crowd do you have? And tweaking these algorithms. A bit of future development. So we only have 30 minutes, so I would love to show you more on the crowd simulation. So I think after this meeting I have to go to the Ask Me Anything. But after that, you can find me upstairs or Jeroen and somewhere here, and we can show you way much more about the crowd simulation. A bit on the future developments. One thing we are running into and we're currently working on is performance. If you have a stadium, you need approximately 18,000 characters. 18, 20,000, depending on your stadium. So we're currently writing parts of the simulation in Rust. Everybody knows Rust? 1, okay, 2, 3, a bit more hands up. Rust is how shall I call it?
Yeah, it's a modern programming language, and it gets to the performance which you have with the C type of languages. So it is compiled, and it is compiled in machine code, and it runs directly on your processor. So it's really fast.
It's really boosting performance. We're going to work on Blender 2.8 and Eevee support, trying to also support a bit more render engines. Looking into a new collision avoidance algorithm that was presented at SIGGRAPH, which uses more a deep learning of neural networks. So that's really interesting. And add more functionality. So leader following, simulating traffic, Boids, ragdoll physics.
You name it.
A lot of things. So there's a lot of work to be done. This is really a first version, at least making it possible to create crowds for stadiums, for instance, or cheering crowds. But there's a lot more work coming up. So I hope you guys will support us. This is something we've also been working on. We've seen at SIGGRAPH, and everybody was like, oh, you guys need to also create a stadium builder. Okay, that's work in progress. Maybe after the performance release, we'll be doing that. I also need to say that a lot of the crowd simulation, we need some fixes in Blender, and we also are patching quite some things in Blender to at least have the crowd simulation running and performing. Yes, it's not a free add-on. So I hope you guys will support us, and that at least we can have a crowd simulation add-on for Blender, and not when I'm at SIGGRAPH anymore. I see a lot of crowd simulations only working on Maya. It would be nice if you have one also working for Blender. Thank you very much.
Mooi.